Welcome back to 10-Minute Science. Last time we built a neuron, but it could only ever draw a straight line. Real neurons aren't like that. They stay off until the input crosses a threshold, then they switch on. Today we give our neuron that switch, and see why depth is useless without it. Here's the proof. 2 plane layers. Look at them. The first multiplies by 2 and adds 1. The second multiplies by 3 and subtracts 1. Let's push a number through. Send in a 4 and follow it across. 2 layers, 2 steps, 1 number out the other side. Now watch closely as we fold the 2 layers together. There. The whole thing just became one simple rule.
And it checks out.
The single rule lands on the exact same answer. So those 2 layers, they bought us nothing. Stack 10, stack 1,000. They always collapse back to one line. A line fed into a line is still a line, no matter how deep you go. That's the problem we have to fix. And a straight line has a hard limit. It can only ever slope one way. Here's real data that breaks it. This is health risk. High when you're too cold, lowest in the middle, high again with a fever. A U-shape. Now, before I draw the line, where do you think it goes wrong?
Watch.
Catch the cold side and the fever side runs backward. One slope can't fit a U. It's worse in 2 dimensions. Blues and golds in opposite corners, completely tangled. Look, no single straight cut can split them. We need a bend. So go inside, 1 neuron. It takes the input, multiplies by its weight, adds a bias, the W and B you see here, and makes 1 number. We call that number the preactivation. Now we insert 1 new step, right after the sum, an activation. Every number has to pass through it before it leaves the neuron. Watch a real value go through. The sum comes out positive, so the activation lets it pass straight through, unchanged. Now, a negative input. This time the sum is negative, and the activation clamps it to 0. The neuron goes silent. And here's the payoff. With that bend sitting between the layers, you can no longer collapse them into one line. Depth finally counts. This activation has a name, ReLU, the rectified linear unit. Look at its shape. Flat 0 on the left, a clean 45-degree ramp on the right. Negatives off, positives straight through. Read it right off the axis. Watch the input step along the bottom. Every negative lands on 0, and every positive comes through unchanged. Now look at how steep the curve is. Flat on the left, slope 0. On the ramp, slope 1. That steepness has a name you'll hear all series, the derivative. But what does it actually do for the neuron? Watch this. Here's what slope really means. I nudge the input, watch the output swing. Now the same nudge over here on the flat side. Nothing. No swing, no signal. The neuron can't even tell it's wrong. Steep, it learns. Flat, it's numb. A dead neuron. 1 ReLU makes exactly 1 bend, a single hinge. Look at the labels. The weight sets how steep it is. The bias sets where it bends. 2 knobs, 1 hinge. Now add a second, a third, each with its own weight and bias, each bending somewhere new. Then sum them up. How many bends do you think it takes to trace this U? Watch. With enough of them, the sum follows the curve exactly, the same curve a straight line couldn't touch. This is the universal approximation theorem. Enough ReLUs in a single hidden layer can fit any continuous shape. But there's a catch. Being able to fit a curve isn't the same as finding it. The right weights still have to be learned, and that's training coming later in the series. ReLU isn't the only choice. Look here. The sigmoid, an S that squashes everything into 0 to 1. And tanh, the same S but centered on 0, running -1 to +1.
3 different bends.
Focus on the sigmoid. Watch the output as I push the input way out to the right. See it flatten against 1? A huge change going in barely moves the output. That's saturation. Now its derivative, its slope. Look, a bell, peaking at just a quarter in the middle, dropping to almost nothing at both tails. Exactly where it saturates, the slope dies. Remember the nudge test? Out here on the sigmoid's flat tails, the slope is nearly zero. So nudge this neuron all you want, the output barely moves. No response, no signal. It's the same dead neuron and it can be badly wrong and still feel nothing. Before ReLU, tanh was the go-to, zero-centered from -1 to +1. The centering helped it train. But look at the tails. They flatten just like the sigmoid. Same saturation, same dead slope at the edges. ReLU has no such tail. On its active side, the slope is always 1, the whole way up. The learning signal never shrinks. That's the first reason it won. And it's dead simple. Just the larger of 0 and the input. No exponentials to compute. Its derivative is only 0 or 1, on or off, nothing between. Cheap to run, stable to train. That's the rest of the story. Now the real problem with sigmoid, deep down. To reach an early layer, those slopes multiply together, layer after layer. Watch how fast that shrinks. A quarter times a quarter times a quarter. It vanishes to almost nothing. That's why sigmoids choke in deep networks. The mechanism, backpropagation, comes later. But sigmoid didn't disappear. It just moved to the output. There, squashing a score into 0 to 1 gives you a probability. The chance an email is spam, the odds a scan is clear. So the rule today, ReLU inside the network, sigmoid often at the very end. ReLU has one weakness too. If a neuron gets stuck on the flat side, its slope is 0 forever. It just dies. The fix is Leaky ReLU. Give the negative side a small slope so it never fully shuts off. And Leaky ReLU is just one of a family. Parameterized ReLU learns its own slope. Smoother cousins like GeLU and Swish are now common in the latest large models. Same idea throughout. A bend that keeps the negative side a little alive. One last piece. If the starting weights are too big, the signal blows up. Too small, it dies out. So we scale them to the number of inputs. That's the initialization. Watch the signal now hold steady across every layer. So make it the rule. From now on, every neuron does 3 things in order. Multiply, add, then bend. That bend is no longer optional. It's what makes a neuron more than a straight line. Now zoom out. Wire thousands of these bending neurons into layers and watch each one add its own fold. The weights set the connections. The bends are what let the whole thing fit a curve. Let's recap. Plain layers collapse to one line. Real data bends, so we insert an activation. ReLU's hinges can build any curve. Its slope of 1 keeps learning alive, and Leaky ReLU plus careful initialization keep it healthy. So our neuron can finally bend, and a network of them can fit almost any shape. But here's the next question. How does it turn that into a decision? When it answers cat, how sure is it? Next time we turn the network's raw scores into real probabilities. That's classification and softmax.
See you then on 10-Minute Science.